Today I will talk about decompiling C++. Decompiling C is more or less solved with Hex-Rays, but C++ is still a bit of a problem. So I will explain today how C++ looks on low level and how to handle it in Hex-Rays. So this is a short outline. I'll describe how classes are laid out, so what are virtual tables, and various kinds of methods, RTTI, and finally how to deal it with in IDA. So some of you probably know the first half. If it's boring, just take a nap or something. So the C++ classes, it's a structure basically combining some data fields with some code. And the data is called fields, and the code are called methods. And we will start by describing how the data part is laid out. So basically, when you have a class and you declare some fields, they are usually laid out in memory sequentially. So if you have such a simple class with two integers, it will have to, basically it's equivalent to a structure with two integers. So the class can be inherited or derived. And when you do this, the parent class, the base class, is basically included in the beginning, and then you have the new data after it. You can also have multiple inheritance in C++. So if you hypothetically make such a class which inherits from both the first simple one and then from the second, which is derived from it, you will actually have two copies of the class A, as you can see. So it will be repeated because the first part will belong to A and the second will belong to B. And because of this, C++ also supports virtual inheritance, which allows you to have only one copy of a base class which is present in several in several other base classes. So in case of this virtual inheritance, because there is only one instance of this virtual base class, the layout is not any more fixed, and the place of this virtual base can change relative to the class it's included in. So how do compilers handle this? It's done by usually by implementing a table of offsets for this concrete class to every virtual base. So Visual C has a separate table for just virtual bases, and in GCC it's combined with virtual function table, which we'll see later. So here's an example, the same inheritance, but with virtual class. As you can see, in the second diagram, there is only one copy of the class A, but it's not anymore at the beginning of the class. It's at the end. And because of that, virtual inheritance gives a bit of a problem when handling it in IDA. So I will describe some tricks how to handle it. And this is this compiler-generated structures for this kind of inheritance. So in Microsoft Visual C, it's called virtual base table, and it's a table of offsets from the actual virtual table pointer to each of the virtual base. So the first 0 is offsets from the virtual table pointer to the class B itself, and the second 8 is the offset from the virtual base pointer to class A. So for example, you can see here that in the class B, the class B itself has virtual table pointer at 0, so the offset is 0, but for class A, it's offset 8. And so if you encounter this kind of structure, you can usually figure out where each virtual base is. And GCC does similar table, but it's put in the virtual function table. In this case, we don't have any virtual methods, so it's the virtual function table is empty, but the offsets to virtual bases are there. So what are virtual tables? If we have virtual methods in a class, the compiler creates a table of pointers to those methods. This is done so that if the method is overridden in a later class, in the derived class, the call in the base class will use this new pointer, new method. This is the point of virtual methods. So to handle this, compiler creates a hidden field in the class, virtual table pointer. It's placed usually at the beginning of the class. And in that table, methods are arranged in the order of declaration. When you inherit from one class to another and you override some methods or add some methods, the compiler creates a new table. It copies the old entries and replaces the new ones, and it will be used in the new class. If you don't override or add any methods, it can reuse the same table. And this table is basically shared among all instances of the same class. So how to recognize method calls? Unlike C, in C++, methods usually take a hidden parameter to a class instance because they need to access members of the class. And this hidden parameter is not explicitly specified in the function prototype. So what compiler does, it just inserts it as a first parameter. In Microsoft Visual C, they have a separate calling convention called thisCall, in which this pointer is put in ECX register. In other compilers, it's usually just the first argument, stack argument or register argument, depending on the actual calling convention. So here's the typical method call. We load ECX from another pointer, and we call a method. So you see the method signature is void, but it actually takes a hidden this argument. And it could correspond to something like line on the below. So we call a method of a pointer, object pointer. Then there are static methods. Static methods, they sort of kind of belong to the class, but they don't really access any of the members of the class. Well, they can access static members which are also shared among all classes. So from the point of view in the assembly code, you cannot really distinguish them from normal functions. So you can only infer from some other signs if it really belongs to that class or not. And you cannot know for sure. Well, in this case, I had symbols, so I can see that this is a method of a class, but it's static because it doesn't take any instance pointers. So it could correspond to a line on below. Then virtual method calls. As I mentioned before, all virtual methods are pointers to virtual methods are placed into a virtual method table. And so the compiler needs to fetch this pointer to this virtual table and fetch the address from it and then do an indirect call. So in this case, we have an instance in the stack variable. So on the first line, we load this instance. On the second line, we load the virtual function table, which is the first member of the class. And then we push the instance, and then we call the third slot in the virtual function table. This is a classic sequence of when you deal with COM code. It's quite likely it's a colony release method on a COM object. And in this case, as you can see, it actually pushes the pointer instead of placing it into ECX. It's done because the COM object model, it does not use this call convention, but uses standard call convention to be compatible with C, because you can implement COM classes in plain C. And this way it's compatible. Then we have a special kind of methods called constructors, which usually initialize object. There's the first code, which is called after we allocate memory. And it usually consists of the following actions. It constructs base classes if it's a derived class. It initializes a virtual table pointer if it has virtual functions. It constructs complex members, so class members which have non-trivial constructors. Then well, C and D are sort of the same because initialization list can also construct complex members. And then it executes finally the constructor body that between the curly braces. Sometimes because of optimizations, very small calls, small constructors can be inlined, and sometimes order of operations can be swapped. So it's not completely fixed, this order. So the calling convention for the constructor is the same as for normal methods, so it accepts a hidden this pointer. And a bit of non-standard behavior from Microsoft Visual C, it returns this pointer from the constructor, although by standard the constructors don't have a return value. And it actually uses this value in the code, so you cannot ignore it. So here's a typical constructor. So you can see in the beginning, it moves the object instance from ECX to ESI. Then it calls a base class constructor. So we can conclude that C machine inherits from C data store object. Then it initializes some fields. And because we can see that it puts a virtual table pointer after initializing the fields, it's probably inlined some constructor for these small members, because if it was the actual constructor, the body written by the program, it would be most likely after initializing virtual table pointer. So how to recognize these constructor calls? There are several ways the C++ classes can be constructed. One of the most common ways is when you declare a local variable, and it's constructed on the stack. So here's a typical construction of a local variable. The address of a stack area is loaded into ECX, and then the constructor is called. So this could correspond to a line on below. We declare a local variable C folder of type C folder string, and we pass an argument. Another way of constructing classes is through so-called heap allocation or new allocation with the new operator. And it's usually quite easy to recognize, because after calling operator new, we test for 0 to check if the memory allocation failed. And if not, then we call the constructor. So this is actually quite a good way to recognize constructors in case you don't have symbols. And in this case, this initial C++ code would look something like the code on the right. So we declare a pointer to C machine object, and we call a new operator to allocate a new instance on a heap. Yet another way of how objects can be constructed is global objects. If you have a global variable which is not a non-trivial object, it should be constructed at the program start or the module start if it's a DLL. So how it's done? Usually the compiler creates a table of small functions which initialize those variables allocated in the data area. And because they also need to be destructed on the program exit, either the destructors are added using @exit calls, or GCC uses a separate table which is also worked the same way as construction table and calls the destructors at the exit time. So here is how it looks usually in Visual C. In the startup code, you have an init term function which takes two pointers, beginning and the end of the table, and it walks through this table and calls each function. And functions usually look like this. It doesn't look very good because of wrapping, but I hope you can read it. So there is a memory allocated in the data area, this variable. We move it to ECX because it's this call convention. We call the constructor. And then it's a Visual C code, so it uses @exit function to schedule a destructor call at exit time. And here's this destructor function, which is called at the exit time. So it also moves the variable address and calls the destructor. GCC does it a bit differently. It has a constructor section with a list of addresses, and destructor sections with a list of addresses. But both those functions in constructors and destructors, they call yet another function with a single parameter, 1 or 0. 1 means construct objects, 0 means destruct objects. And here's how such variable, such a function looks like. So it takes the argument to construct or destruct, and priority you can have in GC, you can have construction priority. It's not really important. And yet another, and I think final way of constructing object is static objects. Static objects, they should be constructed usually during the first use, and the usual way it's done using a guard variable. So in this case, we have a guard variable, and we use the low bit to test if it's if we have constructed the object already or not. So for example, if we have several static objects in the same function, it can use several bits from one variable. This is the way Microsoft Visual C does it. GCC uses a bit different way. It uses special functions provided by C++ ABI. Yes, it was not the final way. It was, we have yet another way, array constructions. When we construct an array of objects, the compiler has to pay special attention because if it has to construct each element of the array separately, but if any of them throws an exception, it has to unwind everything, so it needs to destruct the previously constructed elements. And in Visual C, it's done using a helper function. So this function takes an address of an area for this for the array, then the size of an element, number of elements, and the constructor. And in case it needs to handle exception, it also takes, there's another helper which takes also the destructor. And in this case, it could correspond to something like this. We allocate an array of objects, and we pass a count as the size. Destructors. Destructors is the final code in the object's lifetime. They basically undo what constructors do. They do cleanup and everything. And you can have several constructors, but you can only have single destructor. It also takes a pointer to the object instance, and it does the actions of constructor almost in reverse order, but not quite. So the first thing it does is initialize virtual table pointer, because if you have any virtual calls inside the destructor body, they have to be the calls of the actual class that we are destructing, not of derived class. So that's what it does, the first thing. Then it executes the body of destructor between the curly braces. And then it destructs the complex members and the base classes. And because simple destruct is the same as with constructors, simple functions are usually inlined. So if you have simple destructors of base classes, they will be inlined, and you can have several times the virtual table pointer is reloaded. So here's the typical destructor. So you can see that the first thing it does is sets the virtual table pointer to the actual virtual table pointer of the class. Then it frees some memory, so this is probably the code written by the programmer inside the curly braces. And then it calls the base class destructor. Because it's the last thing it needs to do, it does tail call optimization and jumps to it instead of calling and returning. The situation is a bit more complex with virtual destructors, because you can have virtual destructors. And when you deallocate a pointer to an object, the compiler has to make sure that the correct operator delete is called, because you can, in C++, you can override operator new and operator delete for a class. And in case of polymorphic classes, they can be different for every class in the inheritance tree. And because of that, the compiler has to do something special and to ensure that the operator delete is called actually for this class. So regardless of which pointer type we are deleting, it should call the operator delete of the actual class, not of the pointer type. So Microsoft Visual C does it by making a helper function called so-called deleting destructor, which first destructs the class and calls operator delete of this class. And GCC does it a bit differently. It makes several destructors, and puts them into virtual table. So in virtual table, for Microsoft C, you have a single helper destructor. For GCC, you can usually have two destructors in case of virtual destructors. So here's, for example, how deleting destructor looks for Visual C. It calls the destructor of the class, and then depending on a hidden parameter, it deallocates memory. And it calls, well, in this case, the operator delete was not overridden by the class, so it calls the global operator delete, but it could have been the specific operator delete of this class. And this argument is passed because you can have chained deletions, and only one of them should deallocate the memory. Next is RTTI. RTTI is, it means runtime type information. This is a C++ construct to handle dynamic cast and type ID operators. These operators allow you to check and use the types of objects. So you can have a pointer of one type, but an actual object of derived type. because this is only necessary for polymorphic classes which have virtual functions, virtual methods, it's usually attached to the virtual table. So the compiler puts a hidden pointer into a virtual table. Microsoft Visual C uses a quite complex set of structures. I will just show you one picture, just to give you an idea. For example, this is an RTTI structure for a single class, which implements several functions. I have an article on OpenRC which describes this in detail, so I will not go into it, but it's quite interesting. And you can recover from this set of structures almost completely the class layout. GC does it a bit differently. It puts the actual typeinfo instance as a pointer. Typeinfo is a class which is returned by the type ID operator. And one of the things this typeinfo class has is the mangled name of the class. So basically, if the program uses RTTI, you can recover the class names for every polymorphic class. So it's quite helpful in many cases. So there are some C++ frameworks which do not use standard RTTI, but they use something similar. So it can be also useful when reverse engineering to recover types, names, and sizes, and inheritance. So Microsoft does not use standard RTTI, MFC, Microsoft Foundation classes. All MFC classes inherit from C object, which has as the first virtual method getRuntime class. And this getRuntime class returns a pointer to a cRuntime class instance, and this class basically describes the class, and it has a name, size of the instance, and some functions to create it dynamically, because MFC needs dynamic creation. So this is typical virtual table of MFC class. You see the first method is the getRuntime class, and if you follow it, you will get to this static instance of a cRuntime class, and the first member actually is a pointer to a class name. So you can easily recover class names and also sizes. Then there is Qt framework, which is a popular cross-platform UI solution. It does not use C++ that much, but uses some custom model using signals and slots. And because of this model, it retains quite a lot of metadata, including method names. So not just class names you have, but also method names. And this can be quite convenient. And Daniel Pestelli reversed it quite completely, and he has a very good article and even some scripts to recover this information. So if you ever reverse applications that use Qt, you can go there and it will help you. Then there is another kind of RTTI which is used in Apple IOKit. IOKit is a framework which is used in OS X and iOS kernel to write the drivers. So it might be a bit strange to use C++ in the kernel, but they did it by removing all the not very reliable stuff like exceptions, templates, multiple inheritance, and they leaving only the basic C++ stuff. And they have a separate implementation of RTTI. Again, like MFC, they need to support dynamic creation. And because of that, all classes again inherit from a common object, and they return a meta class instance, and you get an instance size and class name from that instance. And if you follow the meta classes, you can recover quite a lot of information. So this was how C++ works, and now how do we deal with it with IDA, in IDA? In IDA, we have a sort of type system, but it does not support C++ yet. So you don't have inheritance, you don't have virtual functions, you have only basic C structures, that's about it. The Hex-Rays decompiler also does not support C++ specific stuff yet. It supports only C. So we have to emulate C++ constructs using C. So basically, it means that we map classes to structures. Instead of inheritance, we use nested structures. Virtual functions we emulate with a table of function pointers. And if we have any implicit arguments like this pointer, it needs to be specified explicitly for Hex-Rays. So here's how we handle simple inheritance. We create one structure for one class. Then when we inherit, we just put this structure as substructure in the other structure. And this way you can simulate the inheritance, and it works quite well. Then you need to convert implicit arguments for the function prototypes. Sometimes if you have symbols or you got methods some other way from the headers or something, you have the function prototypes, and you might need to convert them to C prototypes. So what you do is for non-static methods, you add this pointer, explicit this pointer, like on the first line. Then if you have a method which returns a structure, you will need to add a hidden return pointer, because that's how it's done on the low level. So the structures are usually returned using a caller-provided pointer. And for static methods, you usually don't need to do anything. Yes, you only need to convert references to pointers. But you don't really need to do it, because IDA will convert automatically references to pointers. So how do you deal with virtual tables in Hex-Rays? You can create a virtual table manually. So if you have virtual tables in the code, you just create a similar structure and rename all the functions, set all the types. You can use the create structure from data command to generate the initial structure. It's not the best way, but it might help. Then you need to rename and set types of all the members. So it can be done manually, but it's might be better to create a small script which parses this function table and creates corresponding structures and puts maybe the types if you have the types. And if you add a repeatable comment with the target address of each function, it can help later if you need to follow a virtual function call. So there are two approaches of handling virtual tables. You can have one table per each class, or you can share one table among one line of inheritance. The first approach is more universal, but it leads to a lot of duplication, because if you recover prototype of one function, you will need to copy the prototype to all the virtual tables which implement the same method. And the second approach is easier because you can share the same table among many classes, but it doesn't work if you have inheritance non-linear, because you will have one kind of methods on one side of the tree and another kind of methods on the other side of the tree at the same offset. So you cannot really share the table in this case. So here's the typical way how it can be done. So we have a virtual table of two methods, deleting destructor and initialize method. We create a structure with two members. We put an address of the method. And we also set the types of the members. And this is how it will look in C-style declaration. So this, for example, this is the same constructors that we've seen before. And here's how we create a structure for it. And it's not shown here, but the CDataStore object is the base class, and it has the first member is the virtual table pointer. And we can set the type of that virtual table pointer to be of our virtual tables that we created before. So if we decompile it with Hex-Rays, it will look similar to this. So you can see that the underscore is the base class. So it's passed to the base constructor. And it also has a virtual table pointer, and it's initialized at the end. And here's an actual call in the code which uses virtual call. So it loads a variable from a pointer, checks it for 0. If it's not 0, then it calls the deleting destructor. And if we use the structures that we created before and set the types for these members, after decompilation, we can see this nice call to the deleting destructor. So this was a simple approach with nesting. It works for simple cases like this, like we've seen before, but it doesn't really work when you have more complex inheritance. For example, we have a single virtual table pointer for both classes, and so we have to choose which virtual table we use. And because of that, we have extra casts and everything. So it also breaks down if you have virtual inheritance, because as I mentioned, virtual bases, they don't really have fixed place in a class, and they sort of move around with every derived class. So another approach that I am adopting recently is to use two structures for each class. One structure, it describes only the fields without virtual table pointers. And another structure describes the complete object. So we include in the complete object this field substructure, and we declare separately virtual table pointers. So here's how it looks like. So we declare a fields structure for the base class for the CDataStore object, and we declare a field structure for the CMachine object. And then we create a complete structure for each of them. So we have a separate virtual table pointer, which we can set type to the actual virtual table used for this or that class. And in CMachine, we include the base class fields and the this class fields. And if we have a third object, like C-session, we again include the base class data store object, and we include fields which belong to just the session class. And this improves things quite a lot, because we can have different virtual tables for different classes, even in the same inheritance hierarchy. So here we have a call which uses cmachine class, and we set the vtable pointer type to the cmachine vtable, and because all the types match, we have no extra casts. And we have a similar call for example, C-session object, and it uses the same kind of virtual calls, but this pointer, the hidden this pointer, needs to be the actual C-session class. And because of that, we need a separate virtual table with separate function prototypes. Oops. And if we use this separate virtual table types, we will have nice decompilation without extra casts. So how do I usually decompile stuff, C++ stuff? Identify constructors and destructors, how I described. So from the global init tables, from the code patterns, from the exception unwinding functions. Then it's better to start from the very base classes. So go down to the most basic constructor, make the structures. If there is a virtual table, create a virtual table structures, set the type of the virtual table pointer, then follow cross references, identify other methods that probably belong to this class, and use those methods to discover maybe extra fields or types of the fields, and fix up the structures. I think I will do a short demo how it works. So here's, for example, a function which uses some constructors. Because I have symbols, it's quite obvious, but even without symbols, you can usually recognize this pattern. You have operator new, then you have a check for 0, and if it's not 0, then it calls a function passing this pointer. So in this case, we can conclude that it's a constructor. So you go to the constructor, and you can see that it calls a base constructor. So you go inside again, and it looks like it's the most base constructor. So Hex-Rays has this helpful menu item called create new structure type, and it automatically fills in the members referenced from this pointer. So we name the structure C data store object, and we can see immediately that the first member is the virtual table pointer, so we can name it correspondingly. And now we need to create a virtual table structure. So we go to the virtual table. We can see that it has two methods, the deleting destructor and initialize. So we go to the structure window and we create this structure. So C data store object virtual table. We create two items, deleting destructor and initialize. And we set the type of our virtual table pointer to the pointer to the structure. If you want to get rid of the cast, you can also go to the table and also set it to this structure. So it will look like this. If we set the pointer types, the offsets, it will look nicer. Okay, this is the base constructor. Then we have derived class. It again adds some more fields. So we also create, we first do reset pointer type, then we create structure type, and we call it correspondingly C global store. And in this case, Hex-Rays doesn't know, but the beginning of this structure should be the base class cDataStore object. So we go to the local types, we copy structure to the database, and we set the beginning of the base class. And I usually rename them like this, just to save on variable names. Okay. Then we can see what it's called, how it's used. We can see that it's moved as the first data item in this object, in this pointer. So we can see where it's used else. And we can see, for example, that here it's used again. The same C global object. Wait a minute. So we can see here that we already have the type set. So the virtual table is recognized and have deleted destructor, but the type is not correct because we didn't set it yet. So Hex-Rays suggests us this type, but it's not completely correct because it did not recognize that it's this call. So it needs an extra, wait a minute. It needs an extra this parameter. Okay. I don't remember exactly how I did it, but I have a ready-made database. Just a moment. Here it is. So this is a database already with all the types recovered. And you can excuse me?
You're setting the convention wrong. It was supposed to be underscore this call, but you were setting underscore this.
Oh, okay. Yeah. So here's already preset type. Here's how it's supposed to be, this call. It accepts an extra this pointer. So once you do this for all your classes, you set types. You can have quite nice decompilation. And this is quite simple example. Let me see if I have something more involved. Yeah, for example, something like this. Yeah, here's an example. I have created a structure for the class with all the fields and virtual tables, and you can see all the calls nicely. So this is not completely C++, but you can have something very close. For example, here's another method that doesn't have a type. If we just set the type, and tell the Hex-Rays to use it. Didn't quite work. Here it is. It returns platform expert, so we will use it. Yeah. So something like this. So the conclusion is that C++ decompilation is a bit more difficult than C decompilation, but it's doable. It helps if you have RTTI and vtables, virtual base tables. You can recover quite a lot of information. Right now, the way I did it was quite manual, but you can automate a lot of stuff, especially handling of virtual tables, setting types, renaming. It's something that we probably will improve at some point. And yeah, there is a lot of things to improve, but it's something that you can do already. Here's some links. The first is the article I have on OpenRC about Microsoft Visual C internals. It describes quite a lot that I didn't describe here. And for GCC, you can consult the official C++ ABI. It describes quite a lot about. And I'm not sure if I have time, but if you want, I have some news about the next version of our decompiler. If you use it, it might be useful for you. So, but if you don't like spoilers, don't listen. Yeah, the first feature that is quite nice we added is variable mapping. So, for example, quite often you have code like this. An incoming argument is copied to a variable, and then we use this variable in other cases. But the decompiler does it because it cannot always prove that these variables will remain the same for the whole lifetime of the function. But if you see from the code that this variable should be the same always, you can map it one to another. And then in all the code, you have only one variable. That's not yet, not everything. Next is the support for unions, which is something which the guys complained yesterday. It's coming. So, for example, this is the kernel structure that uses a lot of unions. For example, here you have automatically, the decompiler automatically picked up something that fits, but it doesn't really know which one is the logical one to use. So, for example, you can see that options is compared with some value. It doesn't make much sense. And you can actually figure out that it should be device I/O control because it's a piece of code from the device I/O control handler. So in this case, you can override manually the decision of the decompiler and use another union member. So in this case, you can see that input buffer length makes much more sense. And the support for some of the idioms used in the Windows kernel, for example, the list entry stuff. We convert this kind of code to the initialize list head. Then we have right now is list empty. And this feature I quite like. If you have a reference from the nested member to the top of the structure, which is done using containing record macro, it's now handled automatically as long as you have proper types on both sides of the assignment. And so it will look like this. And the final thing I would like to mention that we are looking for people to help us with the compiler development. So if you like this talk and you know a bit about compiler theory and you don't mind moving to Belgium, please write us. We would. It's a nice place to work. We have some smart people, I think. So that's it. Thank you.